Throughout my journey to create real working web shooters, there's one thing that has haunted me the most, and that is the trigger system. Throughout all of the web shooters that I've created or anyone has created, the trigger system poses a real problem with creating the functionality that we see in movies and comics. And that is that having a trigger on the palm is a hindrance to movement, to parkour, to travel, to everyday activities.
And it's a hassle. That sounds like a hassle, yeah.
We don't want that. So part of this video will be me continuing to build this electrical, mechanical web shooter that you saw in my last two videos. And the other part of this video will be me creating a sensor that could be used for this device, as well as any other superhero gadget device. And that trigger is just worn on the wrist, as thin as possible. Sort of the prototype that we're seeing in this video isn't as thin as I'd like it to be, but it's a thin band worn on the wrist, and it doesn't hinder the palm or anything like that. So this is what we want to start working toward, is intelligent wearable sensors that can be concealed underneath a device that is itself concealable. And so we don't want to have this clunky mechanical or even electrical trigger on the palm. This is a challenging thing, as you might understand. We're using neural networks, artificial intelligence,
big data analysis, quantum communication, and Internet of Things.
All that crazy stuff to make this happen. So I hope you guys enjoy as I, the amazing, set out to continue my quest toward a really functional mechanical web shooter, a superhero concealable magic trigger. In my last video, you saw me create 7 iterations of some finicky prototypes for this reelable, shootable mechanical web shooter. And you saw my issues with that, Chronicles of Misery, it's what I called the video. It was just a terrible time for me because, nothing was working, but slowly but surely we achieved iteration 7, which had some hints toward that this was actually possible. So moving on from that, we finally got some new motors. We are going to investigate some of the problems that plagued iteration 7. I don't think we're going to number the iterations from now on. It gets a little confusing, but yeah, so let's dive right into this process. All right, hey guys, I hope you are doing well. I have got some new motors here, and I've already put one in, replaced the broken one, and I think it works. Let's see here. Stop. I'm gonna try to fire this line here. That worked pretty well, I think. Probably still a lot of force on the motor. We have some rope that's less friction-y. And we have just an all-around better mechanism now. I do have some pretty big or pretty long M2 screws now. It's possible maybe for me to do this a little bit more eloquently. I'm going to see what I can do in the design. But first I'll test out what I have here. So with the entire device put together, let's do a complete test of the winding and firing. Okay, let's see. By activating this motor, you just make the whole thing shoot out and it pulls out the spool. I don't know. I have my doubts. Let's see. Not great. Not great. It could be because this hit something, I guess. Alright, let's try doing it again. Let's see here. Stop doing that. Gotta wind it this way. Okay. This needs to be fixed. a bunch of stuff needs to be fixed. Okay, let's try to shoot it like up, I guess. Pull the whole thing out. Come on. Okay, still not great. Kind of gross, not gonna lie. Kind of gross. I don't know. It's just not. I guess? Is that it? I don't know. I need a break. So as you can see, this is not going that much better than it was in the previous videos. So in the meantime, let's move over to our B project in this video, which is designing a wearable sensor that can magically interpret signals from around the wrist to decide if your hand is making the correct signal for firing. So to start out, we're looking at analog sensors for this device. So I'm just going to go through all the analog sensors that I have in my laboratory and see what we have available to us, and we're going to decide a way to put them all together. I have one sensor left of these little force sensing resistors here. We got some conductive rubber here. We've got 3 heartbeat sensors. We've got an EMG sensor. I don't think I'll end up using this for this project. This would be very tricky to contain in a small space. It would be interesting as something for a future thing, maybe a Doc-Ock arm controlled with that. But as of right now, I don't think that's going to be useful. Okay, we do have some more FSRs here, some slightly bigger ones. So maybe those will be of use. We have there also one light sensitive resistor here. I'm not sure if that still works. But I think we'll only need one heartbeat sensor. So if we use 2 force sensitive resistors on either side of the heartbeat sensor, and then for conductive rubber, yeah, this is very interesting. As I flex my wrist this way, the shape of my arm changes. But as I flex my wrist like this, it changes almost more dramatically. Right? I get like a big dimple here. And so the resistance between my skin and this band might change slightly depending on how I'm flexing my hand. And that might be something that the AI algorithm could interpret. 2 of these sensors, and this sensor. I have 5 channels. We'll see if we can turn that into some info. If I push this over here, this does come out pretty easily, so that's good. That last test showed me that the mechanisms in the webshooter actually work, but the projectile isn't accelerating enough from the force of the spring to pull out the entire length of the string from the reel. I have a hypothesis that this is because the mechanism that pushes the spring into the projectile, compresses the spring, is also pressing on the release lever before the spring is fully compressed. I videoed me just activating the mechanism manually in slow motion to see at what point is the release lever being pushed to let the projectile release, and is the spring fully compressed at that moment. That is critical for accelerating this projectile to the maximum amount. Throughout these slow-mo tests, I'm manually altering the mechanism, physically altering the mechanism in very slight amounts, slight tuning, so that the lever releases at the exact right time. It's not gonna work. Not gonna work. You know why? Because it never does. Finally, I reached a mechanism that allowed the spring to be fully compressed or nearly fully compressed when the release lever is pressed. All right, we're gonna see if this works now. I'm hopeful, but also skeptical. I've tested the individual subsystems, so we're gonna take this video, and then if something goes wrong, we're gonna watch this video. Bro, come on. Seriously? Why does this never work? Yeah, pretty good. Ugh. Okay, I want to take a moment to address what just happened in these last few tests here. This mechanism here, which is driven by now a pulley system with a mechanical advantage of 3. So the rope goes here and pulls at this point, right? And then it wraps around, so it also pulls at this point, and it also wraps back around here, so it pulls at this point. So it pulls on this object that compresses the spring in 3 places, which means the force on the spring is 3 times the force and the tension of the rope, and the tension of the rope is the force that the motor has to pull. However, that means that, when the projectile gets wound back in, this can't be forced back this way as easy because you require 3 times the friction in the rope in order to pull it backwards. I added another rope that's wound around this spool here. So this one attaches back this way and pulls this backwards as the motor goes back. It's supposed to happen at the exact same speed. This pulley is 3 times smaller than this one. That ended up breaking off. It was pulled all the way, so it couldn't release anymore, and so it was actually pulling backwards on this as the motor was trying to force it that way, and that's why it ended up stalling. And so I replaced it with this much slower motor because I need to buy some more fast motors because I've been going through them like crazy. So I didn't show you the real mechanism that I have here. It works quite well. Very smooth. So that makes me happy. So we can try winding this back in. So this is now, we can't pull backwards, so I'll have to manually do that. Next video I'll make sure to have, so we can see here. This pulley should be releasing the motor, releasing the rope. Yep. So we can attach that and then slowly start to pull this backwards. Come on, there. Yep. So, yeah, you can see this rope has now been pulled. This one here is now shorter because it's been pulled. That's the thing that's supposed to pull this backwards, but we couldn't accomplish that. So I'm just going to trim it for these experiments. So we still haven't added the electronics module with the battery and all the controllers and everything. That will come. I'm still trying to figure out exactly how to make this motor stop because the microcontroller doesn't have room for any more sensors. What am I talking about? Let's see. So the first thing is this reel here that we've seen it, in action. So now it's, it can be coupled there, and we can try to pull in the rope. If we turn on the power supply. I have a much faster motor here as well. You can see the gearbox is smaller than it was at the beginning of this video. So, yeah, it's small but still pretty strong because it's still geared. So just to make that a little bit quicker. And you can see it can pull it all the way in now, which is nice. Maybe not completely all the way, but we're getting close. Like, this whole idea requires so much tolerance, like it's kind of crazy. So this should still be able to fire now. Shoot it off in this direction, maybe. Even with all that tuning, the rope can't be fully pulled off of the reel. So we've got to figure out what's causing this rope to be resisted. In the meantime, let's get back to our sensor design. We have the heart sensor in the middle. We have our force sensitive resistors here. I printed this in Cheetah, NinjaFlex Cheetah. It's stiffer than the NinjaFlex, regular NinjaFlex. And I can't print regular NinjaFlex on this printer right here because it has a Bowden tube. But I think that this design is just too stiff. You can see this is not like a wristband, type thing. I don't like it. It needs to be a lot more flexible to work properly. And yeah, I'm not too sure about, these FSRs here. They're kind of bending outward a little bit. I don't know how much connection they're going to make with the 2 surfaces that sandwich them. So I think we have to redesign this. You can see I didn't even put in the conductive elastic elements here. So yeah, we're gonna redesign this. Luckily, I do have some Ninja Flex, and I also have a new 3D printer. And this one has a direct drive extruder, so we can print Ninja Flex. So we're gonna redesign this to be thinner. We're gonna be a little bit smarter about the way things are attached, and we are going to print it in a less stiff material as well. So I'm excited to see how that turns out. After my redesign of the sensor, I was satisfied with the structure of the material and the flexibility of it, so I decided to add the electronics, which is my favorite part. I'm still uncertain about the stability of these wires coming out of this heart rate monitor, so I decided to add a dab of hot glue to prevent things from wiggling too much and breaking. But I want to reiterate that this is just a prototype, so it's not going to look this tacky, in a few years when we have the final design. All right, so we have finished this prototype sensor here. You can see force sensitive resistor, heartbeat sensor, force sensitive resistor. We've got the elastics hooked up here. I decided to kind of have hooks or hoops around to hold it in place, and that also kind of splits it up, kind of segments it a little bit. Yeah, I have no idea how this is going to work. I figured let's just collect some data and see if there's anything that we can do with it. But before we get to that, let's get back to the mechanical web shooter, which failed because the rope was resisted by something. Yeah, still not. We don't really know what. But I have my suspicions that it's due to vibration of the reel while the rope is being pulled. Because the rope isn't wound around the reel super tightly, as the rope is forcing the reel to rotate, sometimes it's slack, sometimes it's tight, so the reel sort of stops and starts as it's spinning. That creates vibrations, and every time it needs to stop and start again, there's a new acceleration that needs to happen to overcome static friction and the inertia of the reel. And that's not good for the mechanism. That is an energy killer. To test this hypothesis that the rope not being wound super tightly contributes to this vibration, contributes to eating the energy of the projectile, I'm just going to wind the rope tightly manually, even though the web shooter is not capable of that on its own, and see how well the projectile is able to pull the rope off the reel then. You can wind pretty quickly, as long as it's not magnetically attached to anything. And it winds all the way in, or almost all the way in. And I have a really slow motor in here now just for testing. It's possible to have a faster one. But you can see the spring is compressing now. And we're gonna hopefully pull this whole thing out. And as this compresses, this coupling should also disengage. Right? Yes, okay. There we go. See what this can do. Okay. After that test, I think the very last thing that I should probably do is upgrade this reel, because I have this design that just uses sort of steel bearings against steel. So I basically have a bunch of these bushings, steel bushings, press fit into this SLA printed part, and then those go around this screw. The idea is I'm relying on the excessive clearance here to minimize friction. So this bearing is for a 3mm screw, but this screw is 2.5 millimeters. And I think the issue there is that there's a lot of vibration, and you can hear that vibration as it's pulling the rope out. And I think that vibration is not good for the friction, even though this seems really frictionless. So what I think I'm gonna try to do is see if it's any better if I design a reel that looks a little bit more like this with oilite bushings here. These are some oilite bushings that I've had for a while to go around this shoulder screw. and see if we can get a little bit less lubrication, or sorry, a little bit more lubrication, less friction that way. So I wasn't able to pull it all the way out, and I talked a little bit about how there's some friction here that prevents that, because the projectile without the rope can fly very far. Even though like this is so, you know, this is like nothing, but I think it's got to be like the vibrations that happen, you know. So I implemented those brass bearings. They're inside here. You can see it's also smaller, so it can't hold as much rope. I don't know if that's, you know, going to be a permanent problem or a fundamental problem or anything like that. So what I want to do is attach this rope, and first of all see comparatively how much string it can hold and how far that string can be pulled out. Okay, so we can see here that this rope that we were firing earlier from the original reel, this guy, is about, you know, 3 times 18 plus 7, so like 61 inches, probably a little bit more. So more than 5 feet long, right? And it couldn't pull the whole thing out. Could pull almost the whole thing, which is really great. I mean, this is like one of the best performing devices that I've made. I just feel like it could be better. So I want to see how much can be wrapped around this guy right here. Okay, so to my surprise, this reel actually held all 5 feet of the rope. Now this of course is because before I was winding it with this mechanism, and here I was really putting some tension on it, and so maybe a tensioner would actually be a good idea, something out here that grabs onto the rope, and I don't know, this is making the mechanism more complicated of course, but to wrap it really tight, or make sure it's wrapped really tight. I don't know if you guys have another idea of how to do that, but yeah. And then pulling it off is again very, very easy, maybe even less friction, I don't know. Maybe this is worth a shot if we wind it up tight in the back and just see, instead of winding it with the mechanism. Now that the new reel is added, it's ready to test and see if I was correct about friction and vibration eating the energy of the projectile and not allowing the string to be fully pulled off the reel. Spoiler alert, I was right. Before we can test this new reel, let's perform our data collection for our smart wrist sensor. All right, the SD card is not working, so I don't think we'll be able to log data like that. But what we can do is just try to log data with just the serial plotter. First, let's look at the plotter. Okay. Oh, that's not right. Oh, we need to add input pull up to the button. Okay. Input pull up. Yep. And then. Okay, the button's working. FSR, one FSR is working. Other FSR is also working. Can't really, it's hard to tell if the other ones. Heartbeat sensor is definitely working. These guys being stretchy. It looks like they're working. So let's look at the plotter here. Heartbeat sensor looks nice. Yeah, definitely getting stuff out of the stretchy guys too. This is very cool. Okay, let's put it on and just see what it looks like in the waveform. Oh, it's so yeah, it's noisy. When I'm doing this, it goes crazy. To do this data collection, as I said, I've hooked up the 5 sensors. That is the 2 force-sensitive resistors, the 1 heart rate sensor, the 2 pieces of conductive rubber whose resistance will supposedly change and shift as I move my fingers around. To label our data, to show the neural network that we'll be training what should be and shouldn't be a firing signal, I'm going to manually label the data by using my other hand to activate a switch, the switch that you see me activating here. When I'm doing the correct hand signal with the hand wearing the sensor, I will flip the switch with my other hand to tell the neural network that this should be a firing signal. We are collecting data now. don't want to fire here, but we want to fire here, and here, and here, and here. Just like that. Boom, 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 boom. And hopefully, once we've trained the network, it will be able to interpret just the results from the wrist sensor. Okay, we have our stuff saved in a text file here. All the data saved in a text file. That goes from, looks like 1, 2, so 114 million milliseconds, all the way down to, this is good data. Here is where I pressed the, stop pressing the reset button. So we're gonna delete all of that. Okay. So we've got the time, the button, the resist FSR, one stretchy guy, heartbeat, another stretchy guy, and FSR again. I will say the FSRs are not doing a whole lot. This line is an error here. Oh, actually, it looks like it restarted here. So we're gonna erase all of this. The FSRs are not changing at all while I'm doing that. So could be a biasing issue, or issue with the resistor, or the resistor that is in the bridge or the voltage divider. I think we'll be able to do something with it. Very exciting stuff. Okay, that's good. We're gonna see what we can do with this data, but yeah, I hope you guys enjoyed the prototyping process. Now we'll move on to just coding. So the network architecture that I've chosen for the neural network that will activate or learn the sensor signals and interpret it as an output firing or not firing signal is just a simple, fully connected network. We don't want this network to be super wide or super deep, meaning having a lot of weights and biases or parameters, because we want to implement this on a handheld device that will be limited by computation speed. We can't run this on like a huge GPU. So we just want to do a simple model that's just a few layers. What I've done is for each sensor, take a sample of 0.5 seconds. Not super fast, but could be good enough. So each sensor vector, that's the reading of the sensor over a horizon of 0.5 seconds, is converted to a vector and then put through a fully connected network to an embedding. Now each sensor gets its own embedding, and then each embedding is concatenated together into a single vector. That concatenated embedding is put through another fully connected network to create a final embedding of the entire sensor reading, and then that final embedding is put through another fully connected network to generate the output signal, which is just a single number between 0 and 1. And if that number is sort of greater than a certain threshold, I will have enough confidence to say that it is a firing signal. Basically, if it's greater than 0.75 or something like that, I will have the confidence to say it's a firing signal. After coding up this model and the training and the data set, I was able to use the incredible library PyTorch, which is the recommended library for doing neural networks and machine learning with Python. Fantastic library, pretty easy to use once you get the hang of it. But you can see the losses are decreasing. That is, that the error of the network output is decreasing as we keep going with each epoch of training. So you can see in this video that the output of the neural network is not really consistent with the ground truth or the desired output. And that is kind of disheartening to me, and I really wish that it wasn't the case, but it is. But we have to take this and learn from it. And I've noticed some things like one of the force sensitive resistors isn't really activating at all, so it's sort of a dead sensor, not really contributing to the input of the network. And so we have to sort of think about how to improve our data, and part of that is improving sort of our sensor setup, or which sensors we use, where they're placed, that sort of thing. So this still gives me a lot to learn about, and next time hopefully we'll have a better design and better results. Now, why were we doing this in the first place? Oh yeah, that's right. So we can activate an electronic device. We're going to test this new real implementation just to see if it can amplify the performance. We're going to give it its best shot yet. First, we'll just see if we can wrap it all the way tight to
See if it can pull it all the way out. Okay, we're adding tension here. That's the wrong place, bro. Are you kidding me? No, I can't even. This is just the wrong placement of it. It's too far that way. Okay, so this is not gonna reel.
What we're gonna do is wind the string around this reel as tight as we possibly can manually. Even though that this web shooter is not capable of that, we can implement a mechanism that will apply tension on the rope as it's being wound to hopefully make that possible. But right now we're just gonna do it manually, winding it manually, and then firing it to see how well it does in comparison to what we've seen before.
Okay, so it's loaded. We're just gonna try shooting it. We're just gonna see how far we can get it to go. This reel isn't pulling enough. I'm gonna pull it forward. So. I need it. Oh! Okay. So this is very important information for me. That was like butter. My goodness. And of course I was helping it a little bit, but not in any way that I think should matter. And it is actually staying like this now, so I didn't even need to help it. It would have pulled out on its own. So something to keep in mind is that a reel like this is better than a reel like this. I just think I have to make some adjustments here to make sure that this will work properly. But very good things learned all around.
So there you have it. We've made strides with this mechanical web shooter project, a project that when finished will provide a web shooter that can shoot a projectile extremely fast and reel it back in extremely fast. This is a key step toward the swingable web shooter system that I proposed in previous videos. So it's really exciting to me to see this project have a lot more progress than when it was originally started. That being said, we have a long ways to go. This reel mechanism isn't fully implemented yet. We still have to see if it works when the reel is not wound super tightly. And if it doesn't work when the reel is not wound super tightly, we need to figure out how to wind the reel tighter during winding. So some more mechanisms need to be implemented, basically. This project just keeps getting more and more complicated. But anyway, that's fine. That's kind of fun, so it's all cool. And we've also, in this video, created our first prototype for a smart trigger that's just on the wrist, that has no palm interference. And yeah, that is also a big step toward creating a device that can be worn while doing parkour, while doing gymnastics, while doing daily activities even. So that is huge for me personally. I hope you guys realize that I'm ambitious about the science of these projects, about making them the best they can be. And I hope you find that I feel like I'm pretty unique there. So I hope you guys agree. Don't forget to like, subscribe, follow me on Instagram at the.amazing.labs. Support me on Patreon at patreon.com/theamazing. And yeah, I'll be back, guys. I mean, I'm always back. You know me. I never go away, ever. So
I'll be seeing ya.